Okay, pre-calc, our next lesson is going to be about continuity and how we can use limits to test continuity. And so we're going to break this into two pieces. The first part when we talk about continuity at a specific point. So we're going to have some x value we plug in and see what happens. And then we'll talk about continuity of piecewise functions. So we're going to revisit piecewise functions again. So first of all, what does it mean if a function is continuous? Well, a function is going to be continuous provided that when you look at the graph there are no holes, no breaks, and no gaps. In other words, you could draw the entire function without ever having to pick up your pencil. Okay, so holes and breaks like asymptotes are going to create what is called discontinuity, or where we don't have continuous functions. So we're going to need to do three things to see if a function is continuous at C. So this is just some x value, and this is going to be what we approach when we talk about our limits. So the first thing is that f of c exists, and really this means c is in the domain. So when we talk about domain, again, don't forget we can't divide by 0. We can't take the square root of a negative. So c is going to be some value we plug in that doesn't create division by 0, and doesn't take even indexed roots that would be negative. Okay, the second piece then is that the limit exists at c. So again, x is approaching c, f of x, the limit exists. And the last piece then, we're going to test those two pieces. They also have to be equal. So in other words, this just says that step 1 equals step 2. So we're going to do the first part, see if it exists, then we'll find the limit, see if it exists, and as long as those two are also equal to each other, then we can say we're continuous at some point. So an example would be like we have here, a rational function. We're going to look at it at two different values. So at x equals 2, first of all, what we want to do is say, okay, does f of 2 exist? So if I were to plug in 2 in that function, I would actually get 5 over 5, which equals 1. So the first part, we're good. That exists. The second piece, I'm going to look at my limits as x approaches 2 of f of x. And since it doesn't create division by 0 down here, if we plug that in, we can just do our rational property like we looked at last time, and this actually also equals 1. So that's good. And most importantly, because step 1 equals step 2, then we know we are continuous. So we would say we are continuous at x equals 2, because again, these two values are equal. If we looked at x equals 1, well, first of all, we can plug in 1, and if we plug in 1, we're going to end up with 3 over 0. And since we cannot divide by 0, we would say that this does not exist, and since we can't do f of 1, since it does not exist, we would say that we are discontinuous at x equals 1. Okay, there's no point to even check the limit because we already know we're discontinuous at 1 because the value isn't actually in the domain of f of x. Okay, next piece then is when we look at a piecewise function. So you see here we have three pieces, each piece existing on a different interval for x's. So x squared when x is less than 0, 0 to x plus 1, and when we're from 2 to 5, it's 5 minus x. So in order to determine if a function is continuous, it's probably going to be easier to think of where is it discontinuous. So we're going to determine discontinuity, and there we want to think domain. So what values of x do we have to exclude? Okay, second, then we're going to look at each piece individually, and most importantly, by looking at each piece individually, are there any domain restrictions? So this kind of goes with that first piece. And then finally, we have to determine the continuity at the endpoints. So we're going to see, does f exist at each endpoint? So it has to exist here, and the limit exists here, and they are equal. Okay, so going back to that example, first piece, since we have endpoints 0, 2, and 5, what we want to check first is, do we exist at f of 0? So if I take f of 0, that's going to be in this interval, so I'm going to plug it in here, and I get 0. So we exist. Then I need to look at my next value, which is 2, but be careful, when I'm doing 2, I need to plug into this one, because that's where 2 exists. And so I'd have 5 minus 2, that equals 3, so that exists, we're good. And then f of 5, and 5 minus 5 is 0. So we are continuous, or we are existing at each endpoint. So that's good so far. We're on the track to be continuous everywhere. What we need to check next then, so we're going to look at x equals 0. And because this is an endpoint, we're not going to be able to use just one function. Remember, we have to exist from both the left and right. So as x approaches 0 from the left, well, that's when we're less than x, so I have to use x squared. And then I'm also going to look at the limit as x approaches 0 from the right. I meant left up here if I didn't say that. And from the right, and when we are greater than 0, or greater than 0 but really close to it, is x plus 1. So I'm going to write x plus 1 is what we're taking the limit of here. And then we need to plug in and see what those two exist, if they exist. Plugging in 0, I'm going to get 0 squared, which is just 0. And plugging in 0 here, I get 1. And so here, our first problem, we already know that we exist at 0, but the limit as we approach 0 of f of x, since it is not the same from the left and right, does not exist. So we know right now, first part of our answer, we can say we are discontinuous at x equals 0, because our limit was not the same from both sides. Okay, now that's one endpoint, but you'll notice we have another transition point here at 2. We don't need to check 5 because that's an endpoint at the end and there's no transition from one piece to another, but we do need to check 2 still because that does transition from one piece to another. So in order to do that, same idea, I need to say that 2 is approaching from the left and that 2 is approaching from the right. Okay, so 2 from the left is going to be less than, that's x plus 1. And 2 from the right, that's greater than, that's 5 minus x. And if I find the limit of each of those pieces from the left and from the right, I plug in 2, I get 3 here. I plug in 2, I get 3 here. So this is good. This tells us that the limit of f of x as x approaches 2 exists, and it equals 3. In the last piece, it also has to equal f of 2, which if you go back up and look, f of 2 was actually 3. That's what we need for continuity. So since these are all equal, we would say that we are continuous at x equals 2. So the only place we are discontinuous here is x equals 0. So you could say something like discontinuous at 0, x equals 0, or you could say continuous everywhere except for x equals 0. Okay? So that is all about our continuity and limits. So essentially, as a quick recap, we need to figure out does at a certain point at an x value, does the value exist? Is it not in the domain restrictions, in other words? And does the limit exist? And a lot of times we're going to have to check that limit from both the left and the right sides, in particular with our piecewise functions. And then finally, if those first two exist, that's good, but we also have to make sure that they are equal to each other. Okay, see you next time.